Hello, welcome to. That was quite a jump cut, wasn't it? Let's try and do that in a less dramatic. It's supposed to do a little fade. That's better. Hello, welcome to a chill math stream. I'm James. My plan is to just sort of do some maths on Twitch. It's New Year's Eve. Oh, hi Herb. How are you doing? You all right? Did you have a good Christmas? Sort of time. Hi Neutrino. Good Christmas time. It's new. If you're watching a replay or something, we're recording this on New Year's Eve. Recording this on New Year's Eve? It is New Year's Eve. We're not recording it. We are recording it. I found out we've had a week off, and I found out over the break how to get the videos onto Twitch. No, they're on Twitch. How to get them onto YouTube. So. Hi, people watching the YouTube replays. That's now a thing that you can do. Somebody asked on YouTube if I could put them all on YouTube, so we did. I thought that today would be sort of about New Year's resolutions, except. Because this is a maths stream, I'm going to be talking and thinking about what my maths resolution should be. Currently travelling. Maria's, yeah. Twitch is always telling streamers if you want to do Twitch streaming, it's good to be regular. So we do Sunday streams. It's New Year's Eve. We're probably not going to stream up till midnight. That would be obviously very funny. Clock strikes midnight and it turns to 2024. Fun fact which everyone should know is that 2024 is the difference of two squares. That fact is stupid on its own, right? Because let's write it out. Oh, come on, pen. Of two squares. Now this fact is kind of stupid because lots of numbers are the difference of two squares. Maybe you can think of other numbers that are the difference of two squares. But 2024 is the difference. If I stream for 2 hours, which is the plan. Oh, Happy New Year, Neutrino. We could do a countdown at the end if you like. Countdown, and then it's New Year for Neutrino, and then we're off. Then we're off air. So this is a silly fact because the difference of two squares famously factorizes, right? I've run out of space. There we go. Famously factorizes. Normally written out in a horizontal row. Normally written out in a horizontal row, but they're written vertically. And the other way round, anything that factorizes, you can write as the difference of two squares. For example, here's where it would be good to have an example prepared in advance. We'll get there. So maybe I want all of these to be whole numbers. Yeah, probably. If I'm talking about whole numbers, maybe I want all of these to be whole numbers. So anything that factorizes. Now, is there an even odd thing going on here? If I see something like 13 times 2, I want that to be m plus n, and that to be m minus n. Does that get me into any trouble? If I'm trying to work out what m and n are? Well, let's give it a go. So my claim is that this sort of always works. So I can always find these numbers m and n that satisfy these equations and then write, in this case, 26 as the difference of two squares. Yeah, but I think m is going to be sort of 15 over 2, which is not what I wanted, really. Can I improve this? We'll improve it in a second, I suppose. And then this is going to be, what, 11 over 2? I don't love that, but this tells me the fun fact that 26 is the difference of two squares. 15 over 2 squared minus 11 over 2 squared. I suppose if you're going to allow just anything to be the difference of two, to be inside the squares, then of course 26 is the square of root 26 minus 0 squared. So there's something to think about there. Yeah, maybe this is good. When is the sum of... no. So are all numbers the difference of two squares using whole number squares, squares of whole numbers, the normal square numbers. Maybe not all of them. So maybe this fact is interesting. I think I've gone from not interesting a second ago, because everything's the difference of two squares, to, oh, actually 2024 is the difference of two squares in a slightly interesting way. So I'm going to update this to not very interesting, which is somehow damning it with faint praise as a fact. In fact, if I skip through some stuff, then 2024 is actually interesting because it's 45 squared minus 1 squared, which is pretty good. Hi Zoe, how you doing? It's a New Year's Eve stream. We've got New Year's Eve resolutions and facts about the number 2024. I've heard people say that 2024 is the difference of two squares, which is true, and I'm trying to decide whether that fact is interesting or not. My current opinion is that it's not very interesting just to say that's the difference of two squares, because so very many things are the difference of two squares. When does this give me whole numbers on this process? I guess if you know a factorization, then you can do this sort of thing. Add the two numbers together, divide by 2, do the difference of two numbers, divide by 2, and that'll be your numbers to put inside the squares. So really I want them to have the same, what is that, both be odd or both be even? Yeah, okay, so if there's a factorization, if n has a factorization spelling is hard, n1 times n2 or something. Oh, come on, pen. We can do it. We can make it to the new year. n1 times n2, with both of them odd, then it is something like n1 plus n2 over 2 squared minus n1 minus n2 over 2 squared. I think there's a sort of factor of 2 upstairs from squaring. Divided by 2 is 1. Something's not quite right. No, divide by 4 and then take off the other one. Play this one on guitar. Oh, play something on guitar. Ooh, Pulicham musical. Wait, I wasn't reading this. A cool person said do similar thing for the sum of two squares, where you use mod 8, but for the difference of two squares. How does that work? Oh, so for square numbers, a cool is thinking about the remainder when you divide by 8, because, fun fact, all square numbers are either a multiple of 8, or they're one more than a multiple of 8, or they're 4 more than a multiple of 8, and those are the only possibilities. Yeah, those are the only possibilities. But for the difference of two squares, right, could be 3 or 5 or 1 or 7 or 0 or 4. There's sort of lots of possibilities for the difference when you do the remainder. Mod 8. Should we do that fact again? A cool person's mentioned it in chat. So it's a sort of remainder when divided by 8, which is also called mod 8 for short. So you might say something like, it's subtly different. Mod 8 is a much better concept than remainders. Sorry, that sort of distinction annoys me, so it annoys me that I've just said it by mistake. So, for example, in the modulo world, it's acceptable to say that 37 is equivalent to 5 mod 8, but it's just as acceptable to say that 5 is equivalent to 37 mod 8. And this is sort of not how remainders work. When somebody asks you to divide 5 by 8, what's the remainder? You don't say 37. That would be mad behaviour. But in the mod 8 world, everything's nice and symmetric, and you can go. You're not restricted to giving your answers in a particular range. Yeah. So then the fun fact. Let's do the fun fact. So if you look at square numbers, I suppose what we're really doing is thinking about all of the possibilities of what the number might be. The number might itself be a multiple of 8, or it might be one more than a multiple of 8, or 2 more, or 3 more, or, oh my goodness, 4 more, or 5, or 6, or 7 more than a multiple of 8. And those are all the cases for what the number might be. Those are all the cases. I don't need to write 8n plus 8, because that would be a different value of n. It would fall into this first category of things that are multiples of 8. After that many steps, I get around to another multiple of 8. And then squaring all of them. Oh my goodness. There's something called modular arithmetic, which is this kind of mod stuff. There's rules of how arithmetic works, which are all very nice and sensible, which means that you don't actually want to do this kind of thing of like multiply out. I could multiply all of them out and then think about the remainders, but after you've seen a couple, it's not too bad, right? So this is 8 squared n squared, where I can't be bothered to work out 8 squared right now. It's chill maths, chill maths. 2 times 8 times 1. Can't be bothered to double 8 either. Plus 1. This one is 8 squared n squared plus 2 times 8 times 2n plus 2 squared is 4. And there's a kind of pattern here going, which is sort of why modular arithmetic is good, which is that if you're just interested in the remainders or the leftover bits, not worrying about multiples of 8, then you never worry about these kind of, this is a multiple of 8, it's got an 8 in the middle, and so is this. So if you're just interested in the remainder when you do something like this, then you can just look at the last term. Morning, Matt and Ash. How many of these am I going to write out? I think maybe all of them, because we're so very close. So that's nice. So 8 is sort of special. Sometimes when you do this, if you chose a different number instead of 8. Hello. Hoodie, what am I going to do? How am I going to do these vowels in your use thing? I'm going to hoodie magic pants. I might just call you magic pants for fun. Yeah. What's Epsilon limit proofs? That is weirdly enough where I'm going. We're nowhere near yet. 8's a good number because as well as getting this kind of like, here are loads of 8s around, and of course there are loads of 8s when we squared these things. Here are the remainders, and it just turns out that these remainders, 1, 4, 9, 16. Oh, 16 is a multiple of 8 as well. So if I'm ignoring multiples of 8, I can kind of ignore that. 25, 36, and 49. Then the remainders you get, the remainders are 1, 4, 1, 0, 1, 4, 1. It's got this nice pattern. Oh, I forgot this right at the top here. There's a 0 up here. There's no remainder. If it was a multiple of 8 and you squared it, get something that's a multiple of 8. That makes it quite nice. It means if you're then going to add them together, like on that one admissions test question about adding together square numbers, 8 is a good place to look. It's very similar to the sort of calculations you do when you're multiplying large numbers together and you want to find the last digit. You only really care about the last digit of each of the numbers. You've got these massive numbers, and of course you know how to do this multiplication with large numbers thing. You start at, which ends do you start at? You start at that end, right? And you go and you do some sort of like, then you look over here and you multiply by all of the number, and then you look at here and you multiply by all of the number. You sort of break it down into steps, right? But the only bit that affects the units digit on your final answer is what came from multiplying together those. Which end are they on? Not that end. Whatever happened from multiplying those units together in your numbers. Good. I got some feedback recently. I did a talk for some other people, and the feedback I got was that I need to look at the camera a lot more. I need to say a lot less, and I need to get my hands in frame. I don't know. So we're trying out different ways of doing that today. Hi, Mountain Ash. The only difference, of course, is when you learn to multiply numbers together, you're thinking that end. You're thinking about the remainder when you divide by 10. That's a really technical way to talk about it. And of course, it's when you actually do that multiplication, you might get something bigger than 10, which again, that distinction, right? If you're talking about remainders, then that's not technically the remainder, because the remainder is supposed to be less than 10, it's supposed to keep going. But in the world of modular arithmetic, you would say, 27 multiplied by 83 is equivalent to 21 mod 10. Have I heard of the book of Calculus Transcendentals? No, I haven't. I'm looking it up now. Hi, by the way. Welcome to chat. Have we met before? I can't remember if we've met before. Oh, Twitch says you're first time in chat, so hi, welcome to this. I've never seen this. Calculus Early Transcendentals. Is it Ian? Who is this by? That's James Stewart. This one? This one? That's not a really photo, is it? James Stewart as the author? Yes. I have not heard of that book. What's it about? It's about learning calculus. What do the reviews say? Why have I never seen this book? The reviews say, I'm self-studying calculus. This is great. Okay. Cool, we got sidetracked a little bit by square numbers. But... Wrapping it up, I reckon if n is this with both odd or both even, then this is like a way to write n as difference of two squares. Difference of two squares. We're using actual squares. I need to tighten that up a bit to explain what I mean by actual squares, right? But like squares of whole numbers, not like this root 26 nonsense over here, and also not like this 15/2 nonsense over here. So what's that then? That's odd numbers and multiples of 4. I guess this is odd numbers and multiples of 4 means not 2 more than a multiple of 4. There it is again. That's the modular arithmetic. So it's this game. Right, I am going to do... Hoodie, you're doing great. Hoodie's giving me at least 4 suggestions of things to do on stream, which is brilliant. If everyone in chat was like Hoodie, I'd be getting a lot of sidetracks. Perfect squares, that's a good word. I'm going with that, Urban. When I went on somebody else's stream to tell them about maths, I only talked about multi-perfect numbers, and I only showed them that method we were playing with for multiplying numbers together. But I only had 8 minutes, so I talked incredibly fast, and this was just not very good communication. Well, if you've joined us because of that Clopen Mike Night talk, then hi, welcome to the stream. I think I gained 2 followers. Should we do a follower shout out? Calibrated Vision and Shanna Survivor. Thank you for following if you're here. Oh, did you just get rid of Hoodie? Oh no, Zoe. Yeah, you did. Sorry. Absolutely. Was it a Maths Live? It was. What was this thing I was on? So some other maths internet people do a show called Clopen Mike Night. It's got it's a joke on the word Clopen, closed and open. Anyway, never mind. The people on Clopen Mike Night, they get various people along to do 8-minute slots talking about maths things. Mountain Ash has been trying to find a 22/7 perfect number in it. Right, sequencing in chat, backwards first. Yeah. Tell Herb exactly what the number was. It's got to be a multiple of 7, right? Almost pi perfect. The natural number game, I have heard of it. It is not really my cup of tea. I tried to do the first couple of bits of tutorial and realised that it was very fussy, and I'm not very precise. Maybe it could teach me to be more precise. Maybe that's one of my New Year's maths resolutions. Yeah, back to my title. Maybe it should be more precise. I should really spell precise right. Huh. So this is maybe list. Squares. Oh, is that a proof? Squares mod 4 are 0 or 1, so the difference is 0, 1 or 3, so we cannot write things that are 2 more than a multiple of 4, or 2 mod 4 as the difference of 2 squares. Okay. So if you can find a factorization using the difference of 2 squares. So what we've been talking about up here is if you know a factorization, then hey, you can write it as the difference of 2 squares. The other way around is maybe more useful. If you spot that it's the difference of 2 squares, you can factorize it. And this is maybe helpful for... There's something called the quadratic sieve that I want to do. I want to do an episode of Oxford Online Maths Club about the quadratic sieve at some point. That involves me learning a lot about the quadratic sieve. Yeah. You could write that it's 44 times 46, which is kind of cool. Shows you that that's a multiple of... Is that right? Doesn't look right at all, does it? Yeah, doesn't look right at all. 11, 23, these are pretty weird factors. So we've seen before on Chill Maths that once you know the factorization, you can work out that it's the sum of its factors. The sum of factors of 2 cubed 11, 23. I'm just doing this in case it turns out to be a fun number. You do this. You add up all the powers up to that, and all the powers up to its next prime factor, and all the powers of the prime up to that prime factor. Because the factors have to have either a multiple of 23 or not, but definitely not 23 squared. So none of the terms should have 23 squared in them when I add up all the factors, kind of obviously. And they might be even, there might be multiples of 4, there might be multiples of 8, or they might be odd. Those are the possibilities. And if you multiply out this bracket, you get all the combinations. So you get all of the factors. All of this talking is stalling so that I don't have to work out 15 times 12 times 24. So that does look like rather a nice number, doesn't it? Should we do that? It's Christmas, I'm allowed to get a calculator out, which is 4,320. Which is quite a large sum of factors, right? It's about twice as much as the number itself. So, okay, so are we going to say that this is like really close to being a perfect number, but kind of not quite? Is this the clickbait title? 2024 be an almost perfect year. So this will be... Well, let's do it as a fraction, that's more fun. There's no interesting cancellation, is there? I guess there's another factor of 8 here. That's not too bad. So that would give us 253 down here. And it would give us 15 times 12 times 3 up the top, which is 540. 540 is about... so it's 90% perfect in a way. That's within 10% error of 2. So 2024, not a perfect number, but it's pretty close. 2.13, I'll take that. It's pretty nice. It's pretty close to being a perfect number. Question for anybody with access to a computer. Almost perfect year. Here's why: real, not clickbait. If you tell someone it's not clickbait, then yeah, that's how you get them. Oh, by the way, chat's got a new emote for, I believe, followers. So anyone following, we've got a new emote which you use like this. We've got 2 new emotes. we've got a negate symbol, like this, and we've got oh no. Oh no is like the opposite of the wow emote. We already have one for good things happening. Now we have one for bad things happening. Had negate. So you say it's not 2024 yet, or something. Or quadruple not. I wanted the other quantifiers, but Twitch decided these were letters. We're having a bit of a problem getting the emotes that I wanted. We already had these ones banned, and these ones. So hang on. What's that meme? I think, is he wearing glasses? He's not wearing glasses, is he? Maybe he is. He's got hair. He's got his hands out like this. He's got shoulders, I guess. This is like butterfly, but the butterfly has labelled all of these. And this is Twitch. And the subscript underneath will be, is this a letter? Because you're not allowed letters on your emotes. And Twitch rejected the top 4 really quickly. They realised that they realised no, that's bad because letters. And they thought about these two for ages. Have I not done the Y emote? Oh, sorry, I still owe you a Y emote. Twitch. To be honest, it's so that you don't try and spell anything with them. I think Twitch are worried that if you have letter emotes, then you might learn to spell. Can I just drag drop memes in? Does that work? He has got glasses. He has got glasses and way more shirt than I remember. And it's only one hand. He's got like an arm coming out of frame. It's very hard to draw. He's got loads of shirt going on and he's got, glasses. That's terrible. I should stop. That's Twitch. Thanks, Twitch. Right, okay. Maria, I've got to remember to see the Y emote. Cool, right. This won't get me banned, will it? This is fine. It looks more like me than it does like the website I'm on. Right, okay. Don't get banned. Okay, that's an actual New Year's maths resolution. This is fine. Right, I promised some Epsilon stuff. I want to take the mod idea. The mod idea is really good. Once you start meeting this idea about mods, some Epsilons are coming. I'm not going to do analysis, but once you start learning about mod, it turns into this kind of interesting way to identify things together. To say these two different things are actually the same. So, for example, if you have something like the real numbers, but you have modulo, but you do that modulo all the integers. Now, what this means is you take the real number line. I don't know why I've put a start on my real number line. It famously goes in both directions. You take the real number line, but so instead of considering multiples of 8 to all be the same thing, all be 0, you consider all the integers to be the same thing, then what you end up with is something like this, where you have someone standing on the number line, and they can move left or right. There are different real numbers around here. You can explore these real numbers if you like. You can add epsilon. Hooray, epsilon. For all values of epsilon bigger than 0. And you can get to different places. But if you go past an integer, then that's sort of the same as going past this integer over here. If you believe that all of the integers are the same, which is like saying they're all a bit like 0, then that's like also being over here. I've explained that terribly. I'm going to have another go. Okay. So counting if you only look at the last digit, the numbers go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. They kind of loop back around again every 10. What I'm trying to demonstrate is that you can also do that kind of mod 1. So Mountain Ash in chat's calling that mod 1. I'm going somewhere slightly different with this, where the mod notation might let me down. So I'm trying to modulate the whole set. This is pretty good. A diagram that I've seen people draw for this is a kind of loop like this, where you have this point on here marked, I guess, 0 or something. And then this is like 0.5 or something. 0.25 is up here. 0.75. I could be using fractions. Fractions would be nice. So that as you go from 0 to 1, well, by the time you hit the number 1, that's equivalent to 0 if you believe all of the integers to be the same. A weird thing to believe. But if you believe all the integers to be the same, then you can go back round again. And the only thing that matters is the kind of decimal part of your number. People don't often write mod 1, by the way, Mountain Ash. Mod 1, normally the framework for this kind of modular arithmetic is that you were in the integers already. So you were doing integer arithmetic, usually. Not always. There's kind of nothing wrong with writing mod 1 for this. This is what we're up to. Chat. So this is good, but it's still got these kind of, the integers are very familiar. You can do addition of numbers, that's fine. So if you have sort of 1.3 plus 3.9, then you could say that that's equal to 0.2 mod all of the integers. If you don't care about integers, then hey, why not? Of course, in the real world it's about 5.2, but if you believe all the integers to be 0, if you've kind of modulate out. And in a way, this kind of modular arithmetic is a way to, or the wider idea about modulo is a way to ignore certain details, to just look at what's left if you ignore this. Yeah, I have said no mods and then immediately written a mod on the board, but just off screen so you can see it. There we go. Oops. I've never really seen people do this either. So in a sense, if you take R and you quotient out, or sometimes people say quotient out, which is a weird phrase. Let's not analyze it too much. If you quotient out the integers, sort of because this action of doing the modulo stuff is a bit like dividing. Dividing, another word for that is to take the quotient. Never mind. Not take the quotient, right? To use the quotient. Anyway. Other things you can do. So if you say R squared, that's like the plane, like this. Quotient out, so quotient, because people sometimes write the quotient like this. Mods are great. Mods, be nice. I've just set a New Year's resolution not to get banned. So I guess you've got 9.5 hours to ban me if you're going to. Okay. I want to do. Yeah, this notation is not helpful for me to say right now, but sometimes people draw it like a fraction, where I guess we've got ideas about fraction, doing some division and looking at the remainder. So kind of maybe we're not too far away from the idea of having a quotient and a remainder. Quotient out, whatever. If you take the R squared plane and you do a sort of quotient where... How do people write this quotient? How do people write this quotient? I don't know how people write this quotient, but if you take the R-squared plane and you quotient modulo these lines and these lines, that's a terrible way of trying to describe what I'm going on about here. If you quotient in the x direction and in the y direction, so like we were just doing, if you ignore the integer part of both coordinates, so you start with 2D space, loads of room in 2D space, and then you say, well, actually no, I'm going to ignore the integer parts of both coordinates. So these horizontal lines, I'm trying to imagine you have like the line x equals 1 and x equals y equals 1 and y equals 2. You sort of ignore those. And if you also ignore the integer part of your x coordinate, so x equals 1, x equals 2, x equals 3 or something, if you consider those lines to be the same, if you're just looking at the decimal remainder part, not the integer part, then those dotted lines, they correspond to different integers, well, different numbers. But if we're only looking at the bit after the decimal point, they're all the same because they all say 0 afterwards. So if you really believe those to be the same, then what you're left with is, I suppose, just a square over here for the remainders. If you prefer, you could choose a different square, but there's nothing special about that particular square because, of course, they're all the same. But if you're just left with a square with some interesting behaviour. The behaviour is that if you go off this side, you come back over here, because as soon as you touch this wall, then you get back to this point over here. And if you go off this wall, as soon as you touch anywhere on this wall, well, if you keep going upwards, then really that's equivalent to being at a point down here, because I'm ignoring the integer part of your y coordinate as well. It's Pac-Man behaviour. You loop round on both sides. I guess the interesting thing is that if you try and make this out of paper, you try and make a model of this, then you have sort of a square of, if this square which now represents the entire world, and you've got to have this like sort of Pac-Man behaviour that if you come off this edge here is sort of identified with the opposite edge over there. I'm doing them blue. You could write sort of tab A on both of them to join the A tabs together if you're a big fan of IKEA. There's also kind of these edges which we're going to glue together as well. And people sometimes talk about this like glue, that you're sticking things together, that you're imagining that they are the same and therefore need to be stuck together. And people sometimes talk about it like they're identified, or they identify as the same across both sides. And people have seen where I'm going with this, because this is how you sort of famously gets us to some sort of topology idea where this has got the same thing going on as the surface of a torus or a donut. Precise spelling, come on. Torus or donut. How am I going to spell donut? Shall I spell it the British way? That'd be fun. Good. Oh, that didn't film stream. Yeah, so you might be aware of other surfaces, right? That other surfaces exist, and they correspond to other ways of doing the quotient. So I've been really sloppy with notation. I've tried to be obviously sloppy. I think people called me out for this as well. This is obviously not how mathematicians talk about this. I can't remember how to talk about this. Chill maths, right? Chill maths. Hopefully I've been obviously sloppy enough, but there's some subtleties here because you can, depending on how you do the gluing, you can make other shapes. To draw a torus, by the way, who was interested? Mountain Ash was interested in that. The key thing is that you train yourself to draw this shape. U, and then start slightly in a bit. You do an upside down one. It doesn't matter. It doesn't matter how badly you draw that. As long as you miss the end when you're drawing the top bit, miss the end point and stop somewhere else. It doesn't matter how badly you do that. It will look like a donut every time. There you go. there's your secret. You want to draw a double donut, 2 holes in it. You are welcome. It's just art lesson. We've drawn memes. We've drawn donuts. If you take nothing away from the stream, then nothing away from the stream. Wide U shape, go in a bit, join it to somewhere else on there. Hardly matter. You can get it super wrong. Super wrong. Hardly even sort of matters, right? What's an example of doing this sort of badly? Still looks pretty good. Bit wonky, but it's clear. If I'd made that a bit swings and roundabouts. Here for the memes. Looks like a mug to me. So, the fun thing about mugs is that well, if all you care about is some particular things, then donuts and mugs are kind of the same. Has anybody got a mug with sort of 2 handles? So this looks like a mug with 2 handles. There's this way of talking about topology where you either talk about gluing things together, or you talk about sticking extra bits on things. So sticking handles on things is something that topologists do a lot, which I like a lot because it reminds me of the mug donut thing. This is what they teach at Oxford. I have no idea. Probably, yeah. It'd be mad if they didn't. And in fact, there is a course at Oxford on topology. I've never done it. Maybe I should. Maybe I should learn what's actually going on here. I did some sort of topology, right? I remember that something important is that the kind of direction of these lines matters. When you're sticking the B tabs together, you've kind of got a choice. If you stick the B tabs together so that, like this, let me try and draw the behaviour. Pac-Man does not do this. So this is a new behaviour that may be unexplored in video games. Prove me wrong, chat. Then, as you go off the edge like this, you would come back on the top edge, but over here. So this is trying to describe how you go off the bottom and come on the top like that. This is a little bit different. You end up with something different. You end up with a Klein bottle, provided you do the right thing with the A tabs as well. So you get these separate choices for A tabs and B tabs, and this is a way to build a Klein bottle. If you like, a Klein bottle is a torus with a twist, where the twist is in such an awkward direction. the twist so you take your tube that you're playing, this lovely glass tube which you've bent around into a U shape from here, U shape, and then you're going to try and join that side of that bit to that side of that one. I think, yeah. That's really awkward. Which is why they look really awkward. Have I got one here? Oh, I do. Never far away from a Klein bottle. Klein bottles are brilliant. So this one is it's sort of like a 3-point turn in a way. So it's got kind of wide bit around here, which then comes round into a handle at the top. But it's not quite a handle in the same sense. It's a handle in that I can hold it, but anyway, it comes round the top, and this bit is trying to do the kind of 3-point turn. That here it's going up and then it's going down, so it can come back up again. 3-point turn is maybe the worst way of explaining Klein bottles I've ever attempted. I tried to do this once, but explaining. So one way to try and build things like this in your mind, obviously when you're looking at one, it's really interesting, but to try and remember what it's like when it's gone. The thing. Sensation Black, welcome back to chat, by the way. That is excellent. I'm calling that out. That's that. Well done. I worked on this at one point as a way to try and remember what Klein bottles were like. the trick is to try and remember what's going on as you've got to do this twist. So maybe if you took a triangle and you coloured the sides red, yellow, blue, then you could try and spin that around an axis over here. So go whoosh around. And on the way round, if you take that as default, you have your triangle and it goes whoosh and comes back around again, then you get a torus. But if you do a symmetry, so if you do a reflection to the triangle at the same time, like a kind of if you do a reflection on the triangle, then I think you get back to a Klein bottle, but I'm not really sure. Are they chiral? I don't know what that means in terms of a 4D object. Do I? I think they're not. The one I've got in front of me looks really symmetric. Maybe it's not. I think I could topologically deform it into the opposite. Okay. There's a shape I'd really like to understand, which is what happens if you put a twist in both directions. Maybe this should be my... Have I done both twists? I think I've done both twists. Yeah, so that's projective. So is that cross cap or is real projective space? Are they the same thing? Chill Maths, where I try and learn how this works. Trying to remember what a cross cap is. What happens if you identify both the sides like that? I think this is real projective stuff, because now opposite sides of opposite points on the square are now identified. So it's like taking this circle. Squares and circles are kind of the same thing, right? And triangles. It's like taking this and quotienting so that way round and that way round are all the same. Yeah. Is it a pun? Wait, was the bottle part of this? Was the bottle part of this the pun the whole time? Okay. Could be a mistranslation is the other possibility, right? If we don't know. Sorry, if somebody's already looked it up and I missed it, then cool. But mistranslation is always fun. Like the canals on Mars. Canals on Mars is an example. I think an Italian astronomer, see if I can do this story. Italian astronomer sees some lines on the surface of Mars or something. No, I should look it up. It's just misinformation if I try and remember random stuff about Canali. It's something like Canali, right? Let's try and look it up. Why am I so zoomed in? Canali on Mars. Okay, Wikipedia, Martian canals. Great place to be. Whoa, look, it's got maps and stuff. During late 19th, early 20th, erroneously believed there were canals on the planet Mars. There's that little picture of a canal. Oh, I love Wikipedia. Long straight lines, which they could see. Schiaparelli called these canali, which means channels, which was mistranslated to canals. Okay, I got some of that right. Speculation these were engineering works, but later they all turned out to be some sort of complicated optical illusion. So that's a shame. And look, if you mouse over optical illusion, you get a little, what's an optical illusion? You think, oh, one of those. Wikipedia is great. Maria is possibly sarcastically. I had a go, right? You gotta try. And then loads more stuff. Okay, good. Right, we've become a little bit sidetracked, but that's okay. Just a little bit. What was I doing? Oh, I promised some epsilons. Don't really think I've got any epsilons. here's my actual resolution. I would like to understand. This is terrible handwriting. I'm going to have another go. I would like... See, I just get so excited that there's an L coming. That you can see it's doing this kind of... Remain calm. I know there's a good cool L that's going to be in this word, but then just keep it. Way. Okay, right, okay. Handwriting for beginners. I'm not an alien, I promise. I'd like to understand... quotienting out the rationals. It's a bit harder to draw a picture of this. There's some structure left where you, so to be clear, this is real numbers, but all rationals count as 0. So in this world, you could say that pi and pi and a half are now the same, or equivalent or something. And this works. This works because, well, the rationals are nicely behaved subset of the reals. If you add two rationals together, you get a rational. And rationals have inverses and stuff that are also rational. Except, yep, they're just a nice subset. If you have pi and pi and a half, you can add those, and everything's fine. Yeah. So we have no chance of drawing a picture like this. If we draw a picture, it's not going to be like this loop, because there aren't gaps between the rationals. So here's the statement of that in terms of epsilon stuff for Hoodie, in case Hoodie's still here. So for all rational numbers and for all epsilon greater than 0, there exists a real number such that it's really close by, right? The real number and the rational, really close by. There you go. We got an epsilon on stream. So reading this out, this symbol means for all. Twitch have banned it because it looks like a letter. For all q, that's my name for a rational in the set of rational numbers. And for all epsilon bigger than 0. When people are doing this, they don't write out the word and. Oh, never mind. Maybe I should. Maybe if I was being more precise, I'd have a little and operator in here. Or maybe not. They're just quantifiers. They're just brackets, maybe. Yeah, maybe just brackets. Anyway, for all epsilon bigger than 0, maybe I should say that epsilon is bigger than 0. It is real or something. Exists an R such that I think less than epsilon. Yeah, so okay. So there are always real numbers really close by. But this is not the same as saying that everything is the same as each other, because there are still things like root 2 and 0 are different. The difference between them, this is crucial, the difference between them is what matters, and that's irrational. So in a way, this splits up the numbers into rationals, which are now all considered to be 0, and things like root 2 and pi, which are different from 0 because they're irrational. Yeah, no, they do have different cardinalities. There's some chat about how big these sets are, which helps me get away with this. You can actually do quotients on sets of the same cardinality and still get stuff. So cardinality is not the only tool in the toolbox here. There's also interesting things, so like root 2 and pi are still different because root 2 minus pi is irrational. I'm skipping loads of technical stuff here. I hope it's not too weird that I'm counting the rationals as 0. So that's equivalent to looking at the difference between things. If the difference between them is rational, then I say, the difference between them is equivalent to 0, so they're the same. I haven't written out if the difference is equivalent to 0, then they are considered the same in this world. That's kind of what we've been doing all along. Up here we had, if the difference between these things is a multiple of 8, like the next line down that would have been in this list, if the difference between them was a multiple of 8, then I'd consider them equivalent, because the difference is a multiple of 8. And the next one after that would be 8n plus 9, and I would consider that equivalent to this one. So I consider them the same because their difference is a multiple of 8. In a similar way, right, that this line down here, the difference between this and 49 is a multiple of 8, so I'm considering them equivalent. Over here, the difference between these two purple dots is an integer, so I'm considering the same, And over in this really complicated world over here, the reals, but if you count all the rationals as the same, the key thing to do to decide if two things are different or not is to look at the difference between them. This has several challenges. I think this is open. Are pi and e different in this world? Which is a fancy way of saying, is pi minus e rational? I think that's open. I think that nobody knows. I'm going to try and check. It's always you've got to try and stay up to date, right? You can't just keep doing the same. Can't just keep doing the same things. E to the pi. No, everybody's problem with googling e and pi is that loads of maths comes up. Oh, Twitch tech. Yeah, Twitch tech, because then we will be able to do symbols, like all of this cool stuff. I think Hoodie's no longer in chat, right? Are square root 2 and square root 3 different? That's a good question. I've been unable to Google the e minus pi thing. If anybody's got better Google sense than me, I think it's possible that, yeah, people don't know about e plus pi. Whatever. Okay. There's other versions of this, so you might ask about is root 2 minus root 3? Let's do root 3 minus root 2. Different ways you might do that, by the way. So there's a question set in chat by Mountain Ash just now. I think it's not, and I'm going to try and do a proof by contradiction. Not the only Twitch stream with proof by contradiction, but we can give it a go. So I'm going to suppose that root 3 minus 2 is rational and see what happens. I'm being a little bit sloppy. Okay, fine, I'll write it out. With p and q whole numbers, q's not 0, and highest common factor of p and q 1. No common factors or something going on here. Actually, that's important, so let's keep that. Then I guess I want to do something like square both sides. That's normally what you do in this style of proof, right? You square both sides. It's not going to get me all of the way, right? But it's going to get me some of the way. If you're playing along at home, maybe you can see where I'm going with this. So you get square of each term, and you get minus 2 root 6. Yeah. Am I mad? I think so. If they've... I think all of these are the same. I think those are the same. Sure, yeah. If they had some factors in common, that would show up in the highest common factor. And if their highest common factor is 1, then they definitely don't have any common factors, right? Yeah. You can phrase coprime stuff in terms of highest common factors, I think. Yeah. What am I doing? I forgot to square the right hand side. Aha, now here's my target, I think. I've got rational numbers. So I set P over Q to be some sort of set up P over Q to be a rational number. Thank you, Herb. Sorry it took you so long to typeset the squares. Yeah. And I think I want to rearrange this to be like this. Root 6 is 3 plus 2 minus p squared over q squared. Just move all the rational stuff onto the same side. But it's not rational, is it? Root 6 is just definitely not rational. There's a thing for that. I could separately prove it because it's kind of separately interesting, or we could just take it as a chill Sunday maths kind of fact that square roots of whole numbers are either whole numbers or irrational. You can adapt the proof that root 2 is rational. It's a little bit technical and fun, but might leave that as homework. Homework. Root 6 is irrational. We don't really do homework, but when we do. Oh no, the best thing's right at the end of a proof by contradiction. Root 6 is not rational. Handwriting's gone a bit, hasn't it? I've got a new tablet thing. It comes with a pen that I'm not used to at all. Where do we have to start from? So I think you can do this one in a sort of similar way to the root 2 proof, which means you would start by going root 6. Suppose root 6 is p over q. And you might use different letters. I'm not very inventive when it comes to fractions. And then you would go down here. You'd probably square both sides. And you do some really clever arguments to do with, I don't know, multiples of 2 or 3 maybe. And there'd be a bit more maths. And then you'd say, oh no, contradiction. So root 6 is irrational. That is, I think, the shape of the proof. Sometimes it's good to think about what shape it's going to be before you try and fill in the details. I guess that's called having an idea. For me, I suppose it's not having an idea, it's that I've seen this before. What model is it? Oh, what's my tablet? I've got a little Wacom, but I'm not very keen on it yet. I've sort of upgraded in life a tiny bit in that I've got a new tablet from a brand I've heard of. Not a huge fan yet. Hey, it was surprisingly not too expensive. Oh, it's got a box on the back. I haven't seen that before. It's got a little bit for me to write my name. But the pen they give you to write your name with doesn't work at all. Useless. Yeah, it's something like p squared even, right? P squared even. Yeah, it's slightly subtle, right? It's a good exercise because it's like the root 2 thing, but slightly subtle. So you've got p squared is definitely even, but then so what? Because the right hand side is, well, no, hang on. Yeah, no, it's good. It's good. Good choice of the number 2. What's the homework here? The homework is something like the extension to the homework or something. The extension is something like root n is irrational, comma, except when it's not. Come on. Maybe I give myself a tiny bit more. Oh, hello. Yeah, there's proofs like this. Okay, thank you, cool. There's good proofs like this where you have some set of numbers and you prove that at least one of them is irrational. I can't remember if that's the answer to the step question that I'm thinking about. I'm going to find the step question. There's a really good past step question about pi and e and irrational numbers. Where are we going to find this? So it's now trying to use search. Step database is really good. You might be looking for a number, looking for a past step question, and you might find it. There it is. You can find all of the ones up to 2019 on here. Here's the step question. Whoop, there we go. So irrational numbers, and it's, I think, a version of the thing Akul just put in chat, right? So first you prove these statements, and then you show this is not true. And then the fun part of the question is, if the numbers e pi, pi squared, e squared, and e pi are irrational, which I think I believe, by the way, prove that at most one of these numbers is rational, which I like a lot. So your proof has to be something like, if two of these four things are rational, then some stuff happens. And if two of these four things is already 6 different cases, because there are like 42 possibilities of things to look at. But some of them are easy, right? So if two of those 4 things are rational, if, for example, if pi plus e and pi minus e are both rational, then I would simply add them together to get, on the one hand, 2 pi from doing the addition, and on the other hand, just another irrational number from adding them together. Then pi would be rational. So some of them are like that. You say, aha, if these 2 things were rational, then I would calculate this kind of interesting combination to find this other irrational, other rational number contradiction. Really fun question. Yeah. Can transcendental numbers be the solution to polynomials with irrational coefficients? Yeah. Yeah. But only in... Yes, in a really disappointing way, Zoe. You'll hate me. Pi is a solution to x minus pi equals 0. I'm so sorry. This kind of... I think you can only do rubbish like that. You can hide extra roots in there, but... Oh gosh, this is going to be a question about quotienting now. So if you take all the real numbers and you quotient out all of the ones that are roots of polynomials, oh gosh, now you take all the polynomials and you quotient out, there's something here. So I think if pi is a root of a polynomial, then the coefficients sort of involve pi. Maybe not exactly pi, but in a way I can't quite make precise. My feeling is that the coefficients probably just involve pi. I think that one's probably... I think I don't know, but I suspect that... My suspicion is that you can build a bigger polynomial. I don't know how, but I don't know the answer to that one at all. Yeah, so if you've got a polynomial with stuff like root 2 as the coefficients, then that's not rational. But what if that's the coefficient of your polynomial? Now, my feeling is that you won't get pi like that either. How am I going to prove that? Would help if I knew how transcendental numbers work. That would be helpful to say something intelligent on the internet about that question. Good, right, wow. Okay. There was a good example there, by the way. Zoe, thank you. So Zoe asked the question, and I sort of knew what you meant, but also wanted to point out a way, and then you came up with a way to refine it. It's important in research, by the way. important research to be able to come up with a question. Then, if your question doesn't really go anywhere, to modify your question to go somewhere interesting. Right, cool. This step thing's been on screen for long enough. So I think my actual resolution. We'll take a quick break in a second. I think my actual resolution is something like learn integration. I came across these real numbers split up so that the rationals count as the same. I came across them in a really weird context at the very start of an integration course. Let's try and understand. The context is something like you're trying to measure sets of the digits. Mountain Ash, I think transcendental is defined in terms of the coefficients are integers. Oh no, I've googled transcendental and I found a lot of other things. Help, let me Google transcendental number. It's always a shame that wasn't on stream, that would have been funnier. Okay, so I think transcendental numbers are defined in terms of rational coefficients. So he's asking about irrational coefficients, which are which are algebraic themselves. So what would I Google for this? Let's have a go at this. Over here, let's have a go at so it'll be something like. So you can generate interesting ones like this, right? So if you have x squared minus 2 minus root 2 equals 0, then that gives you numbers like the 4th root of 2, which is not the solution to any quadratic. So this is an example of how you can. This is an example of how you can get more interesting solutions by putting algebraic numbers as the coefficients. Of course, that is still algebraic itself because we do this. Can we make? I think we probably can't, chat. I've got a feeling that. What are we doing here? I've got a feeling that the roots of polynomials with algebraic coefficients are algebraic. So, for example, going from, I need to find a way to generalize this, right? To go from this polynomial to this polynomial. So, the numbers that you'll get out here are really just solutions of this regular garden polynomial. Not at all obvious how I would do that. Because, to generalize it, I'd have to say something like if you've got all sorts of nonsense going on. Pi's not a good example. All sorts of nonsense going on. How you could convert that into something else. With boring old coefficients. And that's even, you go even higher than that. Because if I put a 5 over here, then probably that's not even solvable with radicals. So I can't even start to talk about what these roots are. I've got a feeling you just get algebraic numbers out here. Let's do a Google search quickly just to try and close this. Polynomial with algebraic coefficients? Yeah. It covers at least some of the same roots. Right, okay, I think the fact that I'm fishing around is here it is. It's the idea of algebraic closure. This is the math-specific version of my my hunch. So algebraically closed means if you try and make polynomials the solutions, lie in that same set. So the rationals are not algebraically closed because you can have things like x squared minus 2, and the solution to that doesn't lie in the rationals. The real numbers themselves are algebraically closed because, oh no, the complex numbers are Oh my goodness. Do we have to go to complex numbers? Probably do. Are we doing closure? Algebraic closure? Do we have to go to complex numbers? Probably. Fun. How do we prove pi is irrational? I've seen some proofs before, but I've never really understood them. Maybe this is a chance to try and understand a proof that pi is irrational. When I was in sixth form, I saw a proof that pi is irrational, involving like integration and stuff, sort of using A-level maths. Really hard to follow. I printed it out, I think, just stared at it for ages. Not much changes. Still staring at things, printing them out. I'm now trying to find it. I think I'm going to have to come back to it as a future thing. What is this? I'll probably want to do this one on stream at some point. This looks like good chill maths content, right? So apparently this proof was set as an example in an exam at Cambridge in 1945. Let's quickly zoom in. Nope, I don't want Hermite's one, it looks too hard. So something like this, right? Some sort of crazy integration by parts, and then some stuff, and then some more stuff. Suppose pi is rational, then, oh my goodness, right side, oh my goodness, tends to 0, sufficiently large, no it's not a whole number, brilliant, we're done. Achieved by omitting the inductive definition of the function set and taking the time from the present integral. This seems like the sort of thing that I could do on chill maths, but you know. Google says it's complicated. What's this? I can try on other people's proofs. Smallest zero, the sine pi. Oh, that's a nice fact about pi. Ugh. Ugh. What's going on here? Oh my goodness, this looks even weirder. But it's just using integration by parts. It's pretty close because of the substitutions or something. Oh my goodness. Borbacky's proof is an exercise to find this mad integral. But this one looks more like a stab question, right? Repeated integration by parts again. People do it with a lot of integration by parts, apparently, out of all things. What is going on? Oh, okay. Oh my goodness. And here's a recurrent relation. And here's a big claim. And here's some sort of fact about the bound. Oh my goodness. Wikipedia's got several options for a proof that pi is irrational. They all look too hard for me to go through quickly. There's a lot of kind of. So the stories are all from quite a while ago, but the stories are all of the format. Professor X sets a problem on the exam that is essentially new research. Student Y does it in the exam, and later they wrapped it up formally, and that's why we call it the XY theorem or something, right? And that story holds for, I think, more than one thing. The one I'm thinking of is Stokes' theorem. Has that got some sort of connection with a Cambridge exam? Let me try and do the history of Stokes' theorem, which is a good theorem, but anyway. Exam. No, I might have made this up. Some of these are urban legends. Yeah, I really thought, Kelvin-Stokes theorem? Okay. My vague idea is that maybe Stokes' theorem is like that as well. Do they still do this? Not really, I think. It's Green's theorem from an exam. No. One of these. This sort of, well, I think it was 1800s maths, am I right? Oh, roughly correct, I think. But I think it was kind of 1800s maths, late 1800s. Lots of stuff about multivariable calculus. People setting in exams for each other. Good times. What am I doing? I think I'm going to play an ad break to grab a glass of water because I've left all of the water. All of the water is very far away. Oh, some homework. That's a good story as well. I like that too. Proving E is irrational is a step question. Hey, thanks for the redemption. So as a break, a question that I'm always recommending to people is this step question. Page does not want to write a line, so I have to do that, which is just super nice. So E is surprisingly easy to prove it's irrational. This uses the definition, by the way, where you have e to the x is that long power series, powers of x with n factorials downstairs. And if you put in 1, then you get e to the 1, which is the number e. Essentially, those 1 over n factorials get so small so quickly, it sort of converges too fast, is the nonsense thing that people say. It sort of goes really... those leftover bits get small really quickly for too fast for it to be a rational number. I really paused in the middle of that, right? I struggle with a straight face to say, oh yeah, converges too quickly to be rational, because I can converge to a rational number really fast. The sequence 1 half, 1 half, 1 half. How fast do you want it? Okay, I'm going to grab a glass of water because a cool person has told me to hydrate. Am I going to run an ad? I could run an ad. If you want to see this question during the ad break, I think subscribers get to see it, I'm not sure. If you search for 97S3Q7 in the STEP database, which is stepdatabase.maths.org, we'll have a look at this in a second. Ad break. If you see an ad, you're supporting charity. I don't know if it's done it. It might have done it. Oh, it did it. Right. I've no idea how ad breaks work on Twitch. If you're back, let me know. Oh, there's a countdown. 3, 2, 1. Time. I've no idea if they're back. Twitch, eh? What's that like? Lets you run adverts. Doesn't really tell you what's going on while one's happening. If you saw an advert, let me know what the advert was for. Oh, Maria Ranturner is back. Good. Welcome back. Good advert? We're going to... A forgettable advert. A good person's back. Hi, welcome back. Okay. Good adverts or middling adverts? Yeah, I don't control what the adverts are. I think if I get enough, I think the big Twitch players maybe do. How does this question work? So, yeah. Okay, so what do I remember about this question? Bn is a sum you can do because it's geometric. Is the sum nice? Not sure. It can't be that bad, right? Is it just 1 over n? A quick check on Miro. It's first term over 1 minus the ratio, which is going to be... Is it going to cancel? Is it going to cancel? Yes, it is. 1 over n. Good. So then an, each term here is smaller, so it's going to be smaller than the bn's. Okay. And also it's linked to e or something. Headphones and FIFA. Perfect. So you can listen to the football without anybody else hearing it. There's a geometric series on screen right now, Matanash, hiding in plain view. So I think the hard part of this question is going to be part 3. Maybe? No, I think it's fine. Because you do something like you take the expression for e, you multiply it by n factorial, and you get a whole bunch of integers, and then some terms that look like this. Yeah, so this is, by the way, this is the taking away the integer part. This is a bit like r mod z, the real numbers, modulo integers. Oh no, take away the integer part, please. So this is doing the same thing that we just had for our r mod z world. So I think it takes away, there'll be loads of integers at the front for things where n factorial is just so large. And then loads of up to 1 over n factorial, that's a term in the expression for e. E, by the way, is 1 plus, so it's 1 over 0 factorial, which is 1. I shouldn't have said that. That'll just annoy everyone. 1 over 4 factorial and so on. So n factorial e is like huge number plus huge number plus still a whole number, because this just gets out on the bottom bit, plus n factorial over 3 factorial plus dot dot dot, plus eventually you'll get to this thing which is still a whole number, and then this next term will be n plus 1 factorial, which finally the n factorial can't cancel out everything downstairs, so you'll be left with 1 over n plus 1. And then this next thing down here is n plus 2 factorial, which starts n plus 2, n plus 1, and then n factorial starts a chance of getting rid of all of the rest of these terms. So this is an, we're left with integer and an. Oh, and I suppose we need the fact that an is less than 1 as well to mean that this an is definitely less than 1, because an is less than bn is less than 1 over n or something. N is less than bn, which is equal to 1 over n, sorry. Okay, so this leftover part really is the integer, the opposite of the integer, the remainder, when you take out the integers. Okay, well, next, this is part 3, and then part 4, hence show that e is rational. I now think this is the hard part, but I think it's going to go something like, we haven't used the fact that an is bigger than 0, it's going to go like this. Suppose e is p over q, then q factorial e, because I've seen all got these n factorial e things. Q factorial e is a whole number. It's like p factorial p. Sorry, it's p multiplied by almost q factorial. But a q is q factorial e minus the integer part is non-zero, because these ANs are the leftover bits. When you take off the integer part, you multiply e by some huge n factorial, and you get some. It's going great. You get all these integer parts, massive number, all these integer parts. But then you get these leftover fraction bits, and the leftover fraction bits are so small that they don't add up to the next integer. So I guess that's what the meat of the question is. The meat of the question is to look at these ANs, which are the leftover parts, which kind of look like the leftover when you've taken out all the integers, to check that that's smaller than more integer. So check that series converges to something less than 1. So sad news, if you multiply e by n factorial, you will get something that's not a whole number. And that's enough to prove it's irrational. Yeah, slightly different question framing if you put the e higher up and you say... Okay, no, I don't know. I love this question so much. I think this is a really good question. If you're looking for other similar questions in the STEP database, the place to go is stepdatabase.maths.org, which is in here. And so this is what you get if you search for E is irrational in the search box, or just E is. But the search is really powerful. It lets you search for this kind of C1 tag is on ones that are sort of using elementary mathematics in some way. So you can find these ones. Some of them have got fun names, like these ones with characters in. I have some other favourites, but you can go through. Oh, look, really hard simultaneous equations. Are these really hard? No, they look fine. Euclidean geometry. Oh, number theory. So then you see a number theory question, you think, that's all right, but show me a better number theory question, right? I got excited by the phrase number theory, and you see loads of number theory questions. Hey, look, squares, fourth powers. That bit there. Oh, it's not on screen because this is too zoomed in. That bit at the end looks like an Oxford question. That question. Try not to talk about math too much, right? Some STEP questions are terrifying, but some of them are really, really nice. I really like the horse question. Can we do Harry? Yeah, Harry the calculating horse. It's just such a good question. Is it on screen? Has that worked? Yeah, that's kind of worked. It's so good. It's got some. It's a probability question. So how you feel about probability matters a bit here, but it's also just a integration geometry area kind of question. It's got a fun setup, and then the punchline at the end of the question is just, should I get a new horse? Which A+ question writing. I suspect that Harry no longer bothers to do the calculations. Instead there's some random numbers in. Maths is all fine, the horror stories I like less. Okay, we got sidetracked again with just James's favourite STEP questions. The probability ones tend to have a fun kind of context. Yes. In order to get from my money from a cash dispenser, I have to punch in an identification number. I have forgotten it, but I do not know it's equally likely to be one of the numbers from 1 to n. I'm going to punch in integers in order. As soon as I punch in the first wrong number, the police will be alerted. Follow the probability of the police arriving before I get my money is, and then there's some. There's a different variation of it. I like these a lot. Right, I'm really pleased that came up just by searching police in the database. Somebody had tagged it cash dispenser, police. Has not tagged it expectation, but never mind. What's 87S2? Oh, I'm getting requests from chat. 16? Ooh, trees. Ooh. Oh my goodness. I've never seen this one. This is new for me. 87S2 Q16. Oh, they tell the truth. I haven't looked in the fridge. I asked this morning, I would have said it's just as likely to be a body in it as not. Oh, it's so Bayesian stuff, right? Wow. I've now been to look in the fridge, and there is indeed a body in it. Perhaps more than one. Oh my goodness. Right, okay. Is it Bayesian or is it just probability tree? I think it's just tree diagram. Yeah, I think it's just tree diagram. This is amazing. I like. I'm really. Thanks for showing me this. Who? Martin Ash. Just body. Great. With a bit of luck, it's just. I think A plus question, right? It's maybe not helpful in an actual exam with stakes on the line for people to be with a bit of luck. Yeah, you got at least 2 enemies in this question. There's also useless. Yeah, useless Eustace. Useless. So the concept for this question is we're trying to integrate trig functions, and there's a character called Useless Eustace who believes that you can integrate sine to the n by sine to the n plus 1 over n plus 1. And Eustace gets this right sometimes, but very rarely. Off you go. There's a structure of a question around it, of course, which is on the screen now. But this, I got told off in my actual step exam because this question was on my actual step exam, and I got told off for laughing. In hindsight, it's not an extremely funny question, but I was quite stressed, and go in expecting real mathematical challenge. We're going to come up against some really high level concepts, right? Like we're going to maybe a question will be about sums of powers of x, and it'll be based on Fermat's last theorem or something. Then you get into the exam and you see this useless Eustace is rubbish at integration. So oh no. I found out after the exam that Useless Eustace is a cartoon from ages ago. It's like a classic cartoon comic strip character. And Zoe in chat has picked up that this has recently been used by George Eustace. Used not by George Eustace, who's an MP in the UK. I think I can say this on this stream. Probably not on the pro stream, but on the casual stream. I wanted to put Useless Eustace in a question, in a math question for Oxford, because I'd enjoyed Useless Eustace in this question so much. We decided that because of George Eustace MP, partly because of that, and partly because it's not a very good reference, it just didn't need to be there. We decided not to put Useless Eustace in the question, which is a shame. What's the one that's Fermat's last theorem? That's on Fermat numbers, but have we got one on Fermat's? There's definitely a past question that is sort of inspired by Fermat's last theorem. I think it's 2006. I don't know which paper it is. Is it number theory? No, not that one. 5? 4? It's around this sort of time. One ones I did in sort of practice. So 7? No, there's one around here somewhere that's based on powers. That's sort of a special case of Fermat's last theorem. Let's see if we can find that one. Oh look, there it is again. Come round in a circle. I think there is, by the way, some rule about. Well, I'm pointing everyone to the website, so we're good, I think. Maybe I should do all of these. Be a fun thing to say. So I guess, Zoe, the question for you is, if you saw a Useless Eustace, if you saw this question in a step paper in 2024 with Useless Eustace, would you think A, it's a reference to a classic cartoon, B, it's just someone bad at integration called Useless Eustace, or would you think C, this is a reference to my local MP? Market research. So I think a lot of these questions have got the hand of Stephen Siklos in them. By the way, Stephen Siklos was a mathematician at Cambridge who was very involved in STEP, very involved in STEP, and had that sort of sense of humour. B, this is just someone bad at integration, but Mountain Ash would think it's a political comment. Okay, cool. Thanks for the market research chat. So it's but the body in the fridge problem is properly unhinged. I like that one more than what's this one? Body into there. Fine. Properly unhinged. That's brilliant. It's always the second half that gets me. Sort of, you've done some maths, you think, maths, and then I have now been to look in the fridge. There's like a second twist. I now suspect my horse is not actually doing the sums. Immediately B, right, okay, good. Okay. Good to know. What am I doing? Oh, let's find out from the chat command. Thank you everybody who writes messages to the markers, by the way. My favourite ever, which I'm being careful to tell you after Matt, was somebody who just put hashtag Euler at the end of a calculation that had some pies in it. I think it might have had a pi squared over 6 and they put hashtag Euler. Okay. We're setting New Year's maths resolutions. Mine involves integration. So I think my New Year's integration is to learn integration and it's already up there. When did that get up there? And maybe more precisely to learn the Oxford course A4 integration, which doesn't mean anything. So let's put Lebesgue. So I think I can get an early start on my New Year's resolution by learning to spell Lebesgue. Lebesgue. So Lebesgue integration is a way of integrating more functions, stuff that you just can't integrate if your idea of integration is it's a bunch of rectangles underneath the function that tell me how big this thing is. Then there are functions that you just can't integrate because you can't get any rectangles underneath it. But later on in university maths, or later on in history of maths, you learn about Henri Lebesgue. He had a different idea for how to define integration, which my understanding at the moment is that it matches up for functions that you could do Riemann integration on, functions you could do kind of rectangles on. It matches up, it all works fine, but it also lets you define in a sensible, consistent way integration on more interesting functions. They're not just more advanced integration techniques. They let you define new sorts of integral. So an integral is a limit of a sum. It says you take and it says that you take the values of a function and you do some sort of sum, really. I suppose, maybe, and then take some sort of limit of that to assign a value. There are different ways of doing that work in different situations. So in the same way that university is not really about adding together large numbers, but we do have different concepts of addition, and it's not really about dividing large numbers, but we've got all these interesting ideas about how division is actually related to this kind of identifying edges, or related to sticking things together, or glue. Modulo has got these other meanings. In the same way, you don't just learn more integration tricks. In fact, there's not really very many more integration tricks you could learn, but you learn other sorts of integration. Yeah, so Mountain Ash is sort of right to start off with. My route here for 2024 is, if I'm following the Oxford courses, people who have seen the stream before, a few months ago I did this project where I read through all of the Galois theory notes so that I would know Galois theory. It's a sort of self-improvement, self-learning analysis. So it also goes in for these kind of numbered courses. Analysis 1, 2, and 3 in first year. So analysis 1 teaches people about sequences, which you need if you want this kind of, well, if you want to get anywhere with these kind of limiting processes and the limits of things. And analysis 2, which teaches people about continuity and differentiation. And then analysis 3, which does integration with rectangles, which is called Riemannian integration. And it's that thing that you might have seen if you've seen anybody say, well, at university we define integration like this, they'll probably tell you the first way that you learn integration at university. Also in the first year they have this thing called introductory calculus, which is Dan Givotaru did the lectures for this at some point, where you learn a little bit more tricks. So you revise some integration tricks like parts and change variables, but you also learn about partial derivatives, which is a trick for going towards higher dimensions. So differentiation, but higher dimensions. They also do a course, this is still first year, multivariable calculus, which has tricks for integrals in higher dimensions. So instead of integrating on an interval of the real line from A to B, you can integrate across an area. So this is good for finding volumes of things. If you have a shape like this, oh my goodness, drawing skills failing me. If you have a shape like this and you want to find the volume, then you could think about this as a function example. Oh, it's off screen, brilliant, nobody's seen this terrible shape that I've drawn. Instead of integrating over an interval, you can integrate over that thing. But it's still quite boring because you define it at its heart. Boring's harsh. At its heart, it's defined as lots of rectangles, or in this case, maybe cuboids, but still lots of rectangles added together. Things get really interesting in the second year. Can I draw a line onto this? Is this all of the first year calculus? That's kind of all of the first year calculus. Fourier series and partial differential equations as well. A really bad drawing. I thought about not showing you. But it's the second year that I'd like to understand a little bit more, because you learn about metric spaces. So you learn about other sorts of distance. And then there's this course called A4 integration, not like the paper. Integration, which does Lebesgue integration. So here's a function that you can't integrate with rectangles, the kind of way that you might imagine in your head, right? You have a bunch of cuboids or rectangles or something. You have a function made of little rectangles. You make the rectangles very small. The limit gets more appropriate. The limit refines down towards the correct value for the integral. Here's a function that you can't integrate with Riemann integration, but you can integrate with Lebesgue integration. Works like this. The function is piecewise defined, quite a lot of pieces. The function is 1. Let's go f of x over here, sorry. F of x is 1 if x is rational, and 0 if x is not rational. So this is awful. It works as a function, right? You give me a number, f of pi, 0. F of 3, 1. So you can always calculate a value. It's quite a good counterexample, by the way, of something which works as a function, but it's just really not very nice. It's sort of got points up here and also points down here, but the points are... It's really hard to point at the points to draw any kind of picture of it, right? Because you start trying to draw a picture and you think, right, okay, so it's 0 a lot of the time, but it's also 1 a lot of the time. And actually, drawing these points are like the rationals, right? Where x is rational. So really I should not have any gaps. But there are loads of numbers down here sort of splitting apart the rationals and the irrationals. So I try and illustrate it like this. For the second time I've waved my hands in this kind of orientation on the screen. So this function is not integral. You can't integrate this by sticking rectangles underneath it because there's so many points down here. Put these blue points. There's so many points down here that you can't put any rectangles on here. So I can't have 2 lines, but the lines have got kind of gaps in them, which is annoying. So if your plan is to put rectangles underneath it, then there's this height limit on the rectangles, because whenever you try to put a rectangle underneath it, oh no, there are some points down here. So it should be underneath. And whenever you try and put a rectangle over it, then you get something above, and the limits never come together. I'm being vague and not telling you how the limits really work for this, but you shouldn't really be able to expect to integrate this function just by sticking rectangles underneath it. Yeah, is that a function doubler? It's good. I don't think Desmos can plot this, by the way. I don't think Desmos knows about rational numbers. Visually, it would look like 2 straight lines. But I like to imagine it more as dust. There's lots of spots of dust. So Riemann says no. Lebesgue says this integral is 0. And my current understanding let's put in the my current understanding is that you say something like this, that Q is quite a small set of numbers. It's countable, but which means it's really small. Infinite but countable. I think that means it's a measure 0 set, which means that, oh no, this function is mostly 0. This thing happens loads. This one is quite rare. It's got unusual for numbers to be rational. It's much more normal for numbers to be irrational. I think that means the integral is 0 in the Lebesgue sense of integration. I haven't told you anything about how that integration works. I haven't even given you a picture, right? For Riemann integration, I had this idea about rectangles stacked next to each other. I haven't got a picture for you for Lebesgue integration. I think that's my aim for 2024. The tagline is something like this. There's this cool second way of doing integration, which is consistent with everything you learnt at school, but lets you integrate other functions as well. I don't currently have a mental image for it, and I don't know how it works, and I can't actually use it to do any integrals. My aim for 24 is to learn it, so that I've got a little bit more insight into the second kind of integration. I think this is my game plan. I'm going to go back and revise all the analysis and stuff. Don't think I need to revise these 2. And then maybe learn metric spaces a bit better. Read up on Lebesgue integration. Good, it's good to have a plan. What are your plans in chat? What sort of maths do you want to do in 2024? I know lots of people in chat are trying to start university in 2024. So other than 3/4 of the way through the year starting a university degree, what sort of maths do you want to do in 2024? The lovely thing about 2024, if you're finishing school and going into university, is that you've got a big chunk of time in between exams and the start of university. Maybe you've already got plans for that bit. If so, you've got a lovely amount of maths knowledge already. Right, cool. That was an attempt at audience interaction. We'll get there, I got a few recently. Put hands in chat. Maria's not a maths student, just here for fun. Hey, Maria, I'm not a maths student either. I'm just here for fun as well. Yeah, what comes after modular arithmetic? That's a good question. What are you supposed to do next? So, I think you're supposed to do. I'm not supposed to, but I think you could do quadratic residues next. I think. So Mountain Ash is maybe quadratic residues. Maybe I can't spell. So this is the question about which numbers are remainders when you look at the squares modulo some number. You have to understand modular arithmetic first, of course, but then I think you can start looking at this question. Notes on number theory usually have a section on this. So if you find your favourite number theory course, what's supermodular arithmetic? If you just made that up. Set theory in chat. Wait, there's a song about residues, Fermat's Little theorem, and RSA encryption. Where am I going to point Mountain Ash to learn about quadratic reciprocity? Is there an AOPES thing on this? Let me quickly check. Yeah. I don't know if this is a good starting point. No, I've decided it's not. Mountain Ash, this is a thing that I think you could understand given a year. And it's kind of cool. There's a cool theorem here about if you have two primes. And you're asking whether P is a quadratic residue mod Q and whether Q is a quadratic residue mod P. And there's some rules. It's got a lot of proof. It's got some Fermat's-Little theorem. Maybe I should just say Fermat's-Little theorem, right? It's probably Fermat's-Little theorem. Sorry. Oh, when you say FLT, you have to be clear that you mean Little theorem, not last theorem. Fermat's-Little theorem. I like Wilson's theorem. Oh, it's just called Myth Modular. You got me there. I thought that. I suspect it because Stereolab sounds like a real band name, not a maths band name. Mountain Ash, I'd go Fermat's-Little theorem first, Wilson's theorem because it's fun, maybe quadratic stuff. And it's 2 minutes till midnight for Neutrino. Is that true? It's like actually nearly the new year. Yeah, I think it's actually nearly the new year. So, Happy New Year, everyone who celebrates. If you don't celebrate the new year, which I guess is not ridiculous, you might want a different calendar. Those are a thing. Happy New Year to everyone who celebrates. Do you have any maths band recommendations? A bit. I have more songs, right? So, and kind of the obvious ones. So everybody likes Jonathan Coulton's Mandelbrot set. Which I like so much that I would play at work or on outreach things, but you can't because it has swearing. So thanks, Jonathan. There was at school I really like. In hindsight, a lot of the kind of maths nerd parody songs are actually just really bad. This song had a mistake in it originally. Tell me more. In the definition of how the Mandelbrot set works, this song contains a definition of how the Mandelbrot set works, for real. Not just a trap. I think I listened to, I can't remember who recorded this, but somebody did a parody Sound of Friction instead of Sound of Silence. if you're doing a lot of mechanics, I believe somebody did a parody called Sound of Friction. It sounds wrong. There you go. Maybe. Asymptotic. Cool, right, okay. Forgot to do the countdown for Neutrino, but Happy New Year. There's a Tool have done Fibonacci rhythms? No. I'd quite like a song. What's this called? This is an effect. I thought I'd invented this, but it turns out that it's actually a thing. So what I wanted was a song where you've maybe heard the one where a song is pushing it, but the note gets higher and higher. But in the background, a quieter sound gets sort of stages in, so it's got a rising note, but then it's kind of another rising note, and this one starts quiet and gets loud and gets quiet again. So the bit you can hear is always going up, and it's really disconcerting because it's always going up. It's called, I think, barber pole. You can do that with rhythm as well, where you have one rhythm that's getting faster, maybe gradually getting faster, and you have a second quieter one that is at half speed, but then it gets louder and faster as well. So as you tap your foot along to it, the bit that you can hear is always getting faster. I think that might be fun. That's an actual effect that people have tried as well. So there's a kind of I can't spell at all today. There's a kind of speed version. Should I fight heart on the first one, the bubble pole, or on the speed version? Anyway, I just think this would sound really good if you had something that got faster and faster and faster, using this kind of, the bit you can hear is getting faster, and that gradually changes over time using this kind of barber pole effect with loud and quiet things. It's going up, rising, the bit you hear. I think you could make it feel like it was getting really insanely fast. And that's the sort of music I would like to listen to. Speed one, yeah. I saw it in a 2. So I thought it hadn't been done. And then I found it in a, what's that channel called? 2 Violins? 2 Violins. The video is something like 2 Violins Review Audio Paradoxes or something. Is their channel actually called 2 Violins? Let's put it 2, possibly 2 set. Do I want you to? Maybe I do. Yeah. I wanted 2 set violin. Good. Let's see if I can find that, just to wrap up. Audio Paradox. Real test of YouTube search. No, terrible, hasn't worked. Thank you, YouTube search. Okay, I think at some point they listened to a track that was getting faster and faster. 2 set. You've been to a 2 set concert. Right, okay, now I really want to find the 2 set thing that gets faster. What do they call it? Illusions? The thing you see, then it's really hard to find things. Yeah, found it. What a good thumbnail. What a good thumbnail. I should make thumbnails like this. This would be great. They've got a little. How's this made? They've got their 2 faces. They're doing reactions. They've got a symbol and some music and some weird background, and it says "You'll go insane" along the top of the video. These musical illusions will make you question everything. And in the middle of there's this thing that speeds up. Practice. Also works for maths. Right, good, okay. One day. 40 hours a day. This is how I learnt integration. 40 hours, no breaks. Right. There's a drum beat that sounds like it's speeding up. Good, okay. Right, okay, I'm going to watch that after the stream so I can remember what it's called, but I think we have now reached the end of the stream. What have we learned? We did a thing about modular arithmetic and modding out details to see what you have left over. We did a proof that root 3 and root 2 differ by an irrational number. Cool. We did a proof that E is irrational based on a step question. We looked at a whole lot of step questions. Somehow had time to talk about Lebesgue integration, which is that's probably the saddest New Year's resolution anybody's ever set, but there you go. Piano next year. I'm going to look up the name of this thing. Hopefully, Rajneesh finds some thing to do with modular arithmetic. And who is learning set theory? I wrote set theory here because somebody else is learning set theory. Have a good week. I'm going to be back next. Well, I'm back on Thursday for Oxford Online Maths Club. Quick plug for people who haven't heard of the Oxford Online Maths Club. As part of my job, I do a stream like this one on Thursdays at 5 PM UK time. So Thursday 5 PM in the UK. It's online, it's free, it's pretty easy to find, and it's not on Twitch, it's on YouTube, but otherwise pretty similar. And then we're back Sunday for just more nonsense. See you around, Happy New Year, see you next year. Good times. Right. Bye. It's been 2 weeks. I can find the button that switches this off. Found it.